today is actually Valentine's Day, and that heart emoji comes to mind when we talk about Valentine's Day. So actually, heart works on some electric signal, as we know that ions. I am not sure about all these things because I don't have a biology background, but obviously heart works on some electric signals due to those ions in our body and all. So we can say that heart works on has the base of physics, because electrodynamics is a branch of physics. And uh, before throwing some dynamic punches, we start with some static punches. Obviously in boxing we start with static punches, just like that. Before jumping to electrodynamics, we should know about electrostatics. So today we are going to talk about electrostatics, and basically today we are going to talk about basics of electrostatics and some easy things. So let's get started. I am really very excited about this series because obviously I have a soft corner for this branch of physics. So basically we know that charges are of two types. One is positive, one is negative. But how we got to know that this charge is positive or this charge is negative? So we have the convention that the electricity flows along the positive direction. Current flows due to the motion of positive charges. But actually it was that because electrons are small, they can move, and positive charges are obviously. Let me first draw a picture of an atom. So this is still very large, but it should be like this much in size, but I am making it a little bit large. So this is nuclei, actually, sorry, this is nuclei. I have made it a little bit large so that I can explain you this thing. This consists of protons, neutrons. This is nuclei, and here electron orbits in its orbitals, and many of the electrons orbit here. Neutron and proton are just bound by nuclear forces, strong nuclear forces. We know that this strong nuclear force is really very strong to break. That's why if in case we apply some electric field, then electron will go out from this atom, and electron can move. These are bound together and held together. That means it is really very massive. It will require, we know that nuclear force is stronger than that of electrostatic force. Electrostatic force can break this nuclear interaction. Means these things will be kept in a cluster like thing. And if this thing will not break, then proton and neutron can't move, because these will be very massive in comparison to electron. As you know that they have mass of electron has mass of, I guess, 1 by 1800 something times that of mass of a proton or neutron, right? That's why electron is really very small in size, as well as it is not in a cluster of electron. It is independent. So if I apply some electric field, then electron will move, and as electron will move, then obviously the current will flow in the opposite direction of that of electron. We know that previously scientists were thinking that the current flows along the direction of flow of positive charge, but as you can see, positive charges here bound, and in a crystal, or in not in crystal, suppose a rod is made up of ferromine, then these are like, oh, we are really very heavy, we can move. Electron, please you move. And electron is small, so it can pass through those voids and those empty space and will conduct electricity. So basically today we are going to talk about electrostatics, and we are talking about positive and negative charges. From positive and negative charges we got to current. So let's get on to our topic. So positive and negative charges, we are going to talk about Coulomb's law. What is Coulomb's law? Basically it wants to say the electrostatic force between two charges. So this, as we are talking about electrostatics, keep it in mind that Coulomb's law will hold for charges in rest. Charges at rest means if the charges are moving, Coulomb's law is not valid. So let us suppose this is minus q charge, this is plus q charge. So from this we can say that if these two charges are having a high amount of charges, then attraction will increase. Means if the charge is 2q and minus 2q, the charge will increase, and if I change value to half, then the attraction will decrease, right? So we can say that the force of attraction or repulsion, this charge may be positive or negative. That's why we can say that the force may be attractive or repulsive, and the signs are accordingly. If the force is attractive, we will get a negative sign in front of the force, and if it is repulsive, attractive then negative, and repulsive then positive sign in front of the force. So basically we can say that here the force of attraction, the other cases force of repulsion, maybe it depends upon the magnitude of the charges, not on this or this, on both of the charges, magnitude of both of the charges. Let it be q1, let it be q2, and if I decrease the distance between these two charges, then I guess it to be the force of attraction will increase. Means if the distance between the two charges is decreasing, the force of attraction is increasing, I can say that. But what will be the power of the distance? Means I can say that force is inversely proportional to the distance between them, but it is not inversely proportional to distance. It is inversely proportional to square of distance between them. Okay, now I can say that let's remove the proportionality constant and go for equation. Then I will get a proportionality constant k q1 q2 by r square. Actually this is in different branches of physics you will not see that constants. If I use these measurements in CGS unit or SI unit, constants will have the same value. No constants will not change in different units. But in this case, in this electrostatics or electrodynamics, you will be able to see that if I change units, then value of constants will change. So this was actually new to me also, and I want to tell you to that constants will not remain the same in different units. So now we have this thing. So suppose there is not only Q2, I add more charges Q3, Q4, then what will be the net force on this? Let's remove the sign, so that actually the sign doesn't depend upon the whole thing. Means I want to say that if this is q1, let us suppose it is negative and all these are positive. Even if I change the sign here negative, giving it a negative sign, and giving it a positive sign, means if I will take this as vice versa, even then I will get the same result. So I can basically say that you will get the same results even if you change the signs. So actually it was due to the old scientists. because they had the convention that let us say that electron is negative. If I was the scientist and I had said that no, electron is positive, then calculations were have been according to my convention. So all these things are convention only, and you will get the same result even if you change the signs. So now okay, Q1 is surrounded by 3 more charges, Q2, Q3, Q4. So what will be the net force on it? Will force due to Q3, force due to Q3, suppose these all are having a same nature of charge, means positive, then it will repel it along this direction, suppose. Actually yes, another thing that this Coulomb's force is a central force, means the force will act along the line joining the center of two particles. Okay, so the repulsive force will be along this direction, and can you say that will this Q2 affect this force? Obviously no. This is the thing that Q2 will not affect the direction of this force or magnitude of this force. It will apply a different amount of force. It will apply the force something like this, repulsive, and this Q4 will apply the force something like this, and the net force will be resultant of these three forces. And this principle is known as principle of superposition, means the net force on the force on one charge due to the other charge is not affected by some other charge, means force on Q1 due to Q3 is not affected by Q2 or Q4. It is independent of them, but net force on Q1 is sum of all of these forces, means sum of all of the forces working upon it. This is called principle of superposition. And next comes the Gauss equation. So it is actually a really very useful what you say equation, and Gauss law is a law. Yes, it's a really very useful law. And before talking about Gauss law, we are going to talk about electric field, because Gauss law is based upon electric field. So what is electric field? So suppose this is a charge, and here I am going to take a small test charge, unit test charge. I put it here. Now the force will act along this direction and it will repel it. Let us suppose it is positive. We generally take the test charge to be positive and it will repel this positive charge. And now I took this test charge to another position here. It again repelled it along this direction, and I tested it that if I am going to put the test charge, then at different position it will have a different direction force. If I put it in different locations around this charge, then it will get repelled or attracted according to the nature of the charge. And if I draw the lines, if I draw something like this, if I put the test charge here, it will repel something like this. And if I draw a line, like if this thing is here and the force will act along this line, then I will get something like this. And these lines are actually called field lines. Means these are imaginary lines. I will tell you some interesting things about magnets, magnetostatics when I will go to that chapter. But for now, these field lines, I can say that these extends to infinity. Means this line will go to a really very long distance, means its effectiveness can be felt at infinity. Obviously, a very large distance, the magnitude of the force will decrease because F is inversely proportional to r square, but the force will be there. Okay, so actually as we are taking the unit test charge to be positive, here the lines will be away from the charge for a positive charge and towards for a negative charge. Okay, and if here I have a positive charge and here a negative charge, then the field line will originate from positive charge and terminate at negative charge, in case a negative charge is also there. If not, then it will extend till infinity. And the intensity of these field lines will tell us how strong is the force. Like if here I have taken a circle, then here the number of lines per surface area will be number of lines per surface area will be greater than this circle, because here the surface area has increased but the number of field lines is still same. So here the force of attraction will obviously decrease, and here the force per unit test charge, the intensity of the force will decrease, means the force per unit charge will also decrease. And if this thing will decrease, I can say that electric field will decrease, because the force per unit charge is known as electric field intensity. So this is electric field intensity, and we talked about the superposition principle. Okay, now we are going to talk about Gauss law. So basically it states that if I have a closed surface, here I have a charge and it is inside a closed spherical shell, then the total number of electric field lines passing through the surface, which is known as flux or electric flux. What is basically electric flux? Electric flux is the amount of field lines passing through surface area. If here I have a charge here, I have some plane here, then obviously some electric field line will be there due to this charge. How many electric lines are passing through this surface? Perpendicular to the surface. So we have to take, suppose the area vector of the surface is this way, n cap, electric field line is this way. Then if it is making an angle theta with the surface area vector, then I have to take the component, I have to take its cos component, so that it will be perpendicular to the surface. So now it will be equals to E dot dA. Okay, vector. Here I have taken a large surface, but we have to take elemental surface and integrate it to get the total flux throughout this surface. So this is electric flux. So for a closed surface, if the surface is closed, then the integral of E dot dA, this circle means closed integral, means the surface is closed. So E dot dA will be equals to Q by epsilon naught, where epsilon naught is a constant and here Q is the charge enclosed by this surface. Okay, so this is basically Gauss law. This is not for a student doing his or her bachelor's. We'll talk elaborately about Gauss law in upcoming lectures. So this is for today. Actually, this is basic lecture to just make you recall about these basics. So actually this was an introductory lecture, that's why it was a very small lecture, and we just discussed about basics of this electrostatics. In upcoming lecture we will solve some tough questions on basics of this, and then we will proceed to solve those numericals and talk about those equations of that from our bachelor syllabus. So this is for today. Thank you.